Hey everybody, welcome back to Spatial Stats. Pretty exciting, we're starting a new unit right now. This is a unit on point patterns. And so we are gonna change the way of how we think about our observations pretty heavily. So this unit in general is inspired by the book I have up on the screen right now. So this is a whole book. It's got 744 pages of material. And although point pattern analysis can be very mathematical, you introduce things like counting measures, you introduce things like intersections of sets, which is a subset of measure theory. So point pattern can feature measure theory, but it can also be very practical in helping us analyze data. And so we in our class will keep things pretty applied. So if you're interested in the mathematical aspects of point patterns, you won't find it in either this class or in this book. There are plenty of books that do cover that. So 744 pages, of course, I'm not going to cover that in the week or two that we'll be talking about point patterns. I will just try to make you dangerous, to make you, to introduce you to the material, give you some practical tools, give you some code, and sort of set you off on your way. If this is the type of data that you analyze pretty often, I would strongly recommend purchasing this book. Yeah, I don't make any money from advertising. I just think it's a great book. It covers a lot of R as well. It really assumes that you don't know R. So it's a great book, put it that way. Also, we'll be working with a new R package called SpatStat. It's a pretty established, very well established package. It has a lot of its own methods and tools built in because it's been around a very long time. And so we'll be doing most of our analysis with this package. Some of the more modern methods can be found in INLA or INLA. INLA stands, of course, for Integrated Nested Laplace Approximation. Requires a fairly tricky installation. Anyway, most of our analysis will be in the SpatStat package. All right, let's dive in. So we just finished a unit on geostatistical analysis, point reference data, where the coordinates are fixed. They're known, they're fixed, and what is measured at those coordinates is of interest. So we're moving to where the locations themselves, the coordinates themselves, are of interest. And also, the number of locations is a random quantity. So when you are looking at a point pattern analysis, you're looking at a realization. And so a different realization could have the points in a different spot and can have a different number of points. Right? So n is not a fixed quantity. That's something, a whole new world, right? N is not a fixed quantity. In the sense of where we came from in point reference data. Locations are, of course, of interest. So usually X is a covariate here, just to match the notation that exists in a lot of the literature and a lot of the books out there. We'll be using X, this bold X, to denote our observed set of coordinates, our matrix of coordinates. If you think about it, because the locations themselves are of interest, we have an inherently multivariate outcome. What will be bounded and known is this region, spatial region. Sometimes this is called an observation window. And it's sort of how it sounds like. It is the space where you could have observed your points. And just a preview, this is going to be a very, very important concept for us to get the spatial region right. So this is n by d. D is the dimensions that we're working with. So in typical latitude, longitude, easting, northing type data, it's n by 2. Think about disease locations, forest fire locations, where a certain species of bird or tree was reported. But n by 3 is also more than possible. You're thinking of tumor locations. You want to know where they are on your body and how deep to maybe direct a beam of radiation. Earthquake locations. I've seen earthquakes analyzed in 2 dimensions and 3 dimensions. 2 dimensions, that long, but depth of an earthquake is very, very important, of course. So the 3rd dimension can come in. If you think of time as an additional dimension, space-time point processes are a thing. They're just, the methods are not as well developed as they are for just spatial point processes, so we will not be focusing on those. But yes, if you consider time to be a dimension, then you can also have sort of time dimension come into this as well, where you're observing the entire spatial region, the entire domain W at, say, 50 different time points or 10 different years. So that's called the replicated point pattern, and we might get into that towards the end of this unit. All right, it's worth it for us to take a look at some what our authors of the book call the kind of typical assumptions. Typical assumptions. A few of these are less controversial than others. So but a few of these, as I'll point out, sometimes don't happen quite like so. Point unmeasured exactly. Okay, that's pretty good. You know, when you're taking a coordinate, you will assume that that coordinate doesn't lie to you systematically. And no 2 points are in exactly the same location. So of the assumptions that are listed in that first bullet point, this is really the one to watch out for. Sometimes when you're trying to analyze point pattern data, and when we get into the models, you'll kind of, I think, see why you can't have 2 points in exactly the same location. But it will tell you that you have some overlapping points. You have, we only want unique locations. There are not a ton of methods to analyze duplicated points. So you want to remove the duplicated points before analyzing data. And how do you get duplicated points? Well, for disease locations, for example, you might have, it's perfectly possible that you might have multiple diseases in the same, say, high-rise building. For something as common as COVID, that's quite likely. But the way you input that coordinate into R has got to be a little bit different, because you cannot have 2 points in exactly the same location. And you don't want to be analyzing it, you know, with 3 dimensions unless you really know what you're doing there. The next one is another important one. I keep saying the window is very, very important. Well, the window is very, very important because you are assuming that in theory, your points could have occurred anywhere in your observation region, observation window, spatial domain. They could have occurred anywhere. You're assuming you also exhaustively sampled the region. So how does this really play out? Well, here is the bad way of doing it. Oh, you know what? I have some fake lakes on the next slide. Let me illustrate this last assumption a little bit more. Assume that this is a lake. I'm a lake. Very good. You're interested in where is there a specific kind of fish that really you find interesting. Well, you're assuming that the particular kind of fish could have in theory occurred everywhere in the lake. There's not a random dam, for example, that is preventing these fish from getting to this location. You are assuming that your fish of interest could have occurred anywhere in the lake. They could have been here, and then they also maybe could have been here. And the reason they're not here is because there is a drainage pipe that is, you know, pumping sewage out. And your fish don't like being next to sewage. So although it was theoretically possible for them to be near the sewage pipe, they were far less likely to be near the sewage pipe. However, with this last assumption, I'm going to flip back. With this last assumption, you're also assuming that your measurement of the domain of your observation window was exhaustive. And so you, on a boat, yeah, this is arts and crafts time. This is you on a boat with a set of binoculars. Yeah, should have been an art major. This is you on a boat. It's a boat on dry land. You know what they say about boat on dry land. You didn't systematically avoid being next to sewage because you didn't want to pick up some kind of weird, weird disease being next to sewage. So although there is a sewage pipe that is preventing the fish from being close to there, you did sample, here's you in transects sampling this lake. And so, yes, you did observe that there were fish in the north of the lake and the south of the lake, and there were no fish by the sewage. I think I made that perhaps even more clear than it should have been, but it's super important that we are representing our window correctly. Picking up on that. And this would happen if you're say, okay, well, I'm working in my lake. Here's my fish. Very good, I'm ready to analyze. But you forget that, the polygon of the lake might have an island in the middle. Maybe you're in Oregon and this is that Crater Lake, for example, has a nice little island in the middle. So your fish couldn't have possibly been on the island. Your boat could have been on dry land, but fish can't be, how much I know, cannot be on an island, right? So when you're analyzing the data, you have got to represent the window correctly. If there's an island in the middle of your lake, or there are smaller islands in your lake, you have to represent those as sort of holes in your observation window where the fish could not have possibly been, so that you're not interpolating over land for something that is clearly water, right? So make sure that use the correct polygons in your analyses. Continuing with the theme, right? This window has a huge impact on the analyses. It's one of these next few lectures, I'll show you exactly why when we show how to analyze these data. Empty space is super important. This is as good a time as any to direct your attention to the first set of bullet points here. So we only occur where is our fish, where was our fish recorded? We don't, record where it wasn't. Implicitly, because you're only recording the presence of fish, everywhere where you didn't make an observation is an absence. And so you are essentially recording binary data. And so absence is equally informative. And that is why your window is so important, because everywhere where you didn't make an observation inside of your window is an absence of an event. And so, for example, here, suppose your fish like deep water. And if you, for example, misrepresented the shape of your lake, maybe you used a polygon that was not detailed enough to miss this little peninsula. Can't spell peninsula. Again, you really want to correctly represent maybe distance from the shore. If you don't have the bathymetry of the lake, maybe distance from the shore would be an important covariate. Really want to represent that shoreline correctly, because everywhere where your fish are not is absence, and that is super important. Absence. And if you're like, why is this guy still talking about things that are super obvious? There's a major impact on the correctness of your analyses, and I just want to make sure. Okay. Maybe these are things that really confused me when I was first learning this stuff, because I come from the geostatistical kind of lattice aerial data world, and point pattern world I haven't played around with nearly as much. But you guys know, those of you who teach, that the best way to learn something is to have to teach it. So I'm having a great time sort of diving in to point pattern analyses. Spatial covariates. Spatial covariates. Covariates, we tend to think of covariates, for those of you who are not spatial statisticians, you think of covariates as you have your subjects, you have your rows of data, and there's a covariate that is measured for every row of your data. So we're going to go ahead and change our way of thinking, write ourselves a different set of rules. Because, yeah, what artist is that from? Because our spatial covariates must be recorded everywhere and not just at our observed set of locations. With my example where there was a drainage pipe, you can record distance from drainage pipe. With my example where your fish prefer a certain depth of water, you can either record the depth of your lake and use that as a covariate, or you can record the distance from shore as a covariate. But what you actually observe for each fish, things like weight, things like the sex of each fish, things like whether the fish is diseased or not, right? You can have fish be a live fish and dead fish. Some of those move a little faster than others, a little easier to record. But what you are recording about the fish themselves are actually called marks. And what you are recording about your space, about your observation window, are called spatial covariates. So your spatial covariate must happen whether or not there's a point there. And that again comes back to my very first bullet point. The spaces where you don't have an observation are equally informative because they're the absence to the presence. So I thought it's interesting, the authors of the Spatial Stats book and the excerpts they've written, they always go through this exercise where they show the reader what is and isn't a point pattern and highlight all the different interesting features of point pattern analyses. And so this was actually adapted from a different book, if you're curious and you're following along in a book. But this is one of the most classic, I'll just give it away. This is a point pattern. This is a classic example of a point pattern. There are silicon wafers inspected for defects, and locations of defects are recorded. So you have something that looks like a silicon wafer, and you record where there are defects, and you analyze those defects. Maybe you want to know what is the average defect rate. Maybe you want to know if your defects cluster in a particular corner, and that might affect the manufacturing process, how that's all set up. So that's a pretty typical sort of goal for analysis there. So the region, your observation region and dimensions, well, it's as big as the silicon wafer. As big as the wafer. And of course, if the wafers are of different sizes, you have to account for that. Could our events have happened everywhere? Remember, that's an assumption. They could have happened everywhere, but maybe the environmental conditions, thinking back to the fish, pushed the events in a particular location. They could have, these defects could have happened anywhere on our wafers, but they are concentrated in this corner because the machine that manufactures them is messed up in some way. Yes, they could have happened anywhere, where that's the assumption that we're making. That's a reasonable, yes, reasonable assumption. Possible marks and covariates. So I'm saying it like this to drive home the difference between a mark, which is the characteristic of the recorded point, and the covariate, which is the characteristic of your observation window. Covariates happen whether or not you observe the data point there. A possible mark might be the severity of the defect. That's a good thing to record. The size of the defect. A possible covariate would be, I don't know much about the manufacturing process, but the kind of the spatial trend. You know, we're looking at the left-hand side or the right-hand side of the wafer. Are we looking at the top or the bottom? So sort of the spatial trend of the wafer to try and pick out the right-hand side, left-hand side, even the interaction between the X's and the Y's to pick out specific corners. And is this a point pattern? Certainly is a point pattern. All right, let's do something a little bit more interesting, perhaps topical even. Location of violent crimes that occurred in the past week. I'm avoiding time series. Are plotted on a street map of Denver. This is a pretty common application. If you look at point pattern data sets, there's a lot of petty crime, violent crime, different types of crime in different kinds of cities that is out there online. So region W and dimensions. Okay, this is where things get a little bit more interesting. What is the jurisdiction of the police department that you have data from? I'm assuming that you know a little bit about Denver, but we have Aurora and Littleton and Thornton, and whether or not you could have possibly recorded a crime in Aurora defines the region. So if you are only reporting Denver PD data and it couldn't have possibly occurred in Aurora, then you better make sure this is the Denver proper. Denver proper. Are you getting a data from the county? Are you getting a data from the city? Are you getting a data from the state? I don't know, but that has a huge impact on what you would consider to be the observation window. Could you start with Denver proper and then get data from Thornton and Littleton and Aurora? Yes, absolutely. And then your region will change as well. But I said street map of Denver, Denver proper. Could it have happened everywhere in W? Well, again, things get a little bit interesting. What are you recording? Are you recording street addresses? Are you recording lat longs? If this is a street map, that's some grid-like structure. Are you recording that a murder happened inside of a building right here in between the streets? Or are you just recording the street address? And so all of your murders are going to be lined up like this in linear patterns. So if you are doing the first thing, if you're just recording a lat long coordinate and treating your street maps as being continuous, you're sort of disregarding the fact that you have a network, then you are assuming, kind of a network-free space. There is a way, kind of like watch out for events on a linear network. I don't think I will have quite the scope to cover this, but the idea being that the way you would find distances between locations would be quite different as well. We'll be doing a lot of distances. And if what you're recording are addresses, then you better not take Euclidean distances. Or if you do take Euclidean distances, and I think a lot of people do, to sort of simplify the analysis a bit, you make assumptions that it's a continuous surface. Don't overinterpret if your model reports that this, city block is the one with the greatest risk, right there in the middle. Right there in the middle where you're living is the greatest risk. Right? The risk is bound to the streets because that is what you're recording your data on. Possible marks and covariates. Again, this question is designed to promote the understanding of the difference between marks and covariates. A mark is the characteristic of your point that you recorded, and a covariate is the characteristic of the space in which it occurs. So some time ago, a buddy of mine, his family owned a deli in New York City. And apparently what they're worried about is if the deli is too close to a highway, it tends to attract some crime. So a covariate, right, distance to a highway, distance to a nearest highway. How do you define highway? Suppose you define a highway correctly. Distance to a highway is a covariate. Population density of the area is a covariate. Population average age of the area is a covariate. What's a mark? Weapon used. right? That's a characteristic of the event. Type of crime. Was it, who was the victim? Who was the perpetrator? What kind of police response was there? Distance to a police station and the police precinct are covariates. Okay. Is it a spatial point pattern? Yes, it is. Yes, it is. But you can see by the complexity of this very common application of this type of analysis that we have to think long and hard about how we analyze these types of data. Just a super short story. I know we're doing this YouTube thing, but if this were a class, I would tell this story. I went to a conference in Portugal, and they were talking about doing predictive policing. A city of Seattle was considering predictive policing that I believe was using these type of point pattern analysis. And just putting it out there, I want you guys to think through some ethical considerations for making, say, a prediction of risk across the city. And what neighborhoods would that point to? And whether or not that's wrong or right, what is the correct response? What is the correct policy response? And even farther away from my comfort zone is what are the legal implications, right? Of plain sight. What are the legal implications of filling the streets with police officers because your statistical model has predicted that risk was going to be high in a particular area? Just kind of putting that out there. Predictive policing. I am unaware of the status of this, but I know there were cities in this country that were considering using this approach. Please don't quote me on it. I know this is going out into the world, and everyone will be watching this video, but that is absolutely an application that I think I would be not doing my job if I didn't mention. Moving on. Seismology. Seismology is a huge part of your day if you live in the great state of California. If you're, I think, one of the 39 million people, that's a lot of people that live in this great state of California, or internationally in Japan. I'm thinking of active fault lines. Alaska just had a major earthquake reported. South America, Chile, and Peru have a lot of earthquakes. If you are near an active fault, you care deeply about seismology, or you should. So here, location and depth of earthquakes over the past year, again, I'm avoiding the time series aspect, recorded in the state of California. Region and dimensions. Well, I said California, so again, what is the authority in which you're getting your data from? Earthquakes tend to occur near, at least natural earthquakes, tend to occur near fault lines. So are you just getting the fault lines, sort of intersecting the fault lines with the political boundaries of California? So California. The way I've phrased the question, the answer is California. Realistically, you would have to think about where you're getting your data. If you're getting your data from the United States USGS, you probably have it on, outside of California as well. That might be a more accurate representation of risk than just limiting yourself to the fault lines in California. But if you're working for an insurance company in California, you only care about California because your policies only apply to California. Could have happened everywhere in your observation window. So that's a good one, right? In theory, can an earthquake happen everywhere? I'm not a geologist, and I think geologists would fight me on it, but I will say the answer is yes in theory. Ask about earthquakes away from fault lines in places like Oklahoma. Yes, in theory. But we must account for the fault lines or other risk factors for earthquakes. Possible marks and covariates. Well, a covariate, again, is a characteristic of the space, characteristic of a window. So covariate very well might be distance from fault line. A possible mark might be the magnitude of the earthquake. And also location and depth. I have 3 dimensions here, right? Because I have the latitude and the longitude and how deep was the earthquake. So if I really have these data, I better make sure and use methods for 3-dimensional point pattern analysis. Is this a spatial point pattern? Yes, it is. How would I turn this into not being a point pattern? If I was instead holding the locations constant and analyzing the magnitudes instead, right? Here are my locations of where earthquakes have happened. And so what I'm measuring at my locations is the magnitude of each earthquake. If I have the type of data, maybe the amount of casualties, the amount of injuries an earthquake has caused. Again, I'm holding the conditional on these exact locations. I can now analyze the spatial patterns in this quantitative response of, you know, how many casualties, how many injuries, how much money did it cost, what was the magnitude. But if what I want to show is I want to predict where are there hotspots for earthquakes. The keyword there is where. When I'm interested in the where, I'm talking about a point process, a point pattern. All right, moving right along. This is a ballot measure, not about to tell you how to vote. If you're in Colorado, they're thinking about reintroducing gray wolves into Colorado. I'm just supposing that you might want to fit them with GPS collars and track their locations every hour, every day for a year. Well, the region and dimensions is Colorado and Wyoming. Could we have observed our gray wolves everywhere? In theory. Again, in theory. Do I expect to see a wolf in the middle of downtown Fort Collins? No, but can it happen in theory in the middle of the night? Yes. How can I account for the propensity of wolves to stay away from people? I can find the major population centers, take the distance from every major population center, and use that as a spatial covariate. So again, I'm sort of modeling how you would account for these types of influences. So I'll say yes, in theory. You have to sort of measure the habitat of your wolves. Maybe, you know, maybe they're more likely near ranchers who have things for them to eat. I don't know. Possible marks and covariates. I've discussed a few of the covariates. Possible marks are things like the sex of the wolf. The age of the wolf. The weight of the wolf. Maybe that's what you're concerned about, you know, keeping them healthy. Is this a spatial point pattern? All right. The answer is no. And here's why. We have to go back up here where I bolded something. And the key was that our point pattern is assumed to be unordered. We can flip around the order in which our points were observed, and it shouldn't influence the outcome. We assume there is no order to the points. If what I'm recording are the location of the wolves, what I will be recording is their migration patterns. You know, maybe they're walking around, you know. That is definitely an ordered set because the locations, these locations, are ordered they are not a point process. Oh boy. Oh boy. There we go. Because these locations are ordered, the location of the wolf today would be highly correlated to the location of each wolf yesterday. There's clearly an order to the locations. You cannot analyze them using the point process methods. What if you analyze a lot of animal movement data? That's a whole separate set of methods that are specialized to that particular field and not really in the scope of this class. There are a separate set of R packages that analyze animal movement data. Or I suppose you could treat these as at least a correlated point pattern, which too, the methods are a little bit outside the scope of an introductory spatial stats class. If I had a class on point patterns, a full semester-long class on point patterns, we would definitely get into analyzing this. I know for my audience, some of you are analyzing these type of data. So, look up packages specifically for that. Unfortunately, point patterns, maybe some of the exploratory things, but we're assuming that our points are going to be unordered. And that doesn't work for animal movement, based on how animals move. All right. Location of UFO sightings. I had an undergraduate student last spring analyze the point patterns of UFO sightings. She did a great job. And so there's a database out there where the location of each UFO sighting is recorded. I think most recently, even every month. And so maybe we're finally trying to catch them. We're trying to get them. So the region and the dimensions, of course, the United States has Alaska and Hawaii, has a protector of Puerto Rico. So you have to really think about your data. If your data does not only covers the continental US, then you better just, make the continental US your observation window. If you have data in Hawaii and Alaska, then you better cover those states as well. If you have data that it occurs somewhere in the ocean between the islands of Hawaii, you got to include that data. So I hope you can see that this stuff is complicated. And you have to represent your observation window correctly. So some subset of the US. Could our locations have happened everywhere? Well, I'm no UFO expert, but we're not talking about a UFO landing on Earth. I think we could probably say it is possible for a UFO to come down and land on Earth. They could take a sample of the soil and then blast off back to where they come from. Planet Omicron 27. Just made that up. So although the presence of UFOs is probably possible everywhere on Earth, including where there are no people, sightings depend on people. So populated areas only. And you know what that means? Think back to our crime data. People rarely walk in the middle of a field away from roads. UFO sightings, and there are plenty, are still going to be concentrated around roads. Yep, people do camp in the Rocky Mountain National Park, look up and say, there's the UFO, there it's coming for me. But the vast majority of these are going to be concentrated around linear networks. Maybe that's why we haven't caught them yet, because they like to go in the middle of the Pacific Ocean where there are no people. Starting conspiracy theories. Possible marks is maybe the shape. That's actually a variable. The shape of the reported sighting, the duration of the sighting. But what about covariates? That's again a characteristic of the space in which our event occurs. Maybe it's distance to road. Maybe it's elevation. Maybe these things happen at a higher rate at higher elevations. Maybe it's distance to a military base. Okay. All right. So those are just 5 different scenarios that I wanted to think through with you guys to sort of just get us thinking about what is and isn't a point pattern. Goals of analysis. We can be analyzing either the underlying intensity, and again, intensity is just basically a rate. It's the expected number of points per unit area. Think of it as like a spatial rate. We can be either analyzing the underlying intensity, the interaction between the points, or both intensity and the interaction between points. So the underlying intensity is called first order effect sometimes. So you think of this as sort of there is some underlying surface that you don't get to observe, but these events are more likely where the intensity is higher and less likely where your intensity is lower. So this is really most of the time how we will build our models. Based on the pattern of our observed events, we will build models for the log of intensity. Intensity is non-negative. The smallest it could be is 0, where there are no events and very unlikely to observe an event. So we will be building models on this log scale. Correlation is generally ignored. This will be clear when I show you how we put the models together. We don't account for correlation generally inside of the likelihood. The exception being there are, of course, models that do account for correlation between nearby observations, about nearby intensity predictions. And it just takes our entire geostatistical unit and ports it right into this world. Why shouldn't nearby coordinates share some information about the underlying risk of a UFO? And of course, we were going to focus on modeling later in our unit. You can instead focus on the interaction between points. So the interaction between points is sometimes referred to as the second order effects. It's a concept, extending the concept of correlation to point pattern analysis. It's possible that if you have some kind of an infectious process or some kind of a flowering plant, naturally, you're going to have more points around, or the risk of observing an event is going to be higher around existing events. That is different than saying the conditions in humid, warm climates are more conducive to a virus happening, a disease happening. No, this is saying that if I have an infectious disease, I'm focusing on potential interaction between 2 diseased cases. Now, of course, we can only gather so much about the mechanics, but I'm trying to illustrate the difference between focusing on the environmental conditions that are conducive to development of disease and focusing on the interaction between diseased cases, and that the risk might be higher around existing cases. We anchor our analysis on the existing cases. Note that we can model both positive and negative correlation. And how does negative correlation occur? Well, it's possible if you have competition among species that it happens around trees. If there's a particularly tall tree, it will sort of drive away other species of trees around it for some trees. And so that is indicative of a negative correlation. Positive correlation is a clustering. It's an attraction. There is something that encourages new events to happen around old events, as opposed to repulsion, where when you have an event, chances are reduced that you will have another event around it. Here is a nice figure from this book. I did not make this figure, but this is a very nice figure that illustrates the difference between first order effects and second order effects, right? So if we're looking at the location of different kinds of trees, we have 3 kinds of trees. Here's a quiz. What the type of tree is what? The mark. It's a mark. Gradient and soil type, what is it? What is that? Gradient and soil type are covariates, spatial covariates, right? They happen whether or not there's a tree there. So there's the gradient is really high here. Maybe that's why we don't see the trees. And the gradient in soil type, maybe even the moisture levels, are high here. Gradient is low, moisture level is high. Different soil type, maybe it is more conducive to a specific kind of trees. If you're using distance from this lake as a covariate, it's really good for these willow trees, right? But it seems to be have a negative association with these oak trees, the way this picture was drawn. All of that is a first order, analyzing first order effects. Second order effect says, well, these suppose are flowering trees. And so clearly the seeds are more likely to be spread around the trees and have other of the same kind of tree grow in the vicinity. The difference between first order and second order effects. I hear you saying, well, but can I analyze them both? Can I analyze them both? And the answer is, generally, it's very difficult. We are generally asked to pick either focusing on the underlying intensity, first order effects, or interaction between points. You can analyze them both, but it's hard because of confounding. And specifically, it's the positive correlation component. A model cannot tell apart whether the clustering, the apparent clustering, is due to a spatial trend. If you have clustering in a corner, is that because there is a spatial trend with respect to both X and Y? Or is that because you have an infective case right there, and so that infected case spread the disease to other people around it? A model cannot tell those two mechanisms apart. And so if you include both intensity and interaction in the model, you will have spurious estimates, large standard errors, or even a lack of convergence. Now, I think it's more promising, though of course it's very case specific, if you have different kinds of patterns. So for example, your first order effects are accounting for like large scale environmental conditions, and your interactions are accounting for repulsion. So a negative correlation as opposed to a positive correlation. It's the clustering that is the problem here. Or it is more promising if you're able to observe replicates, which again, I keep mentioning, but it's still fairly uncommon for us to observe replicates of the entire point pattern. It's expensive to obtain an exhaustive survey of your entire observation window. I found a lot to talk about in the first 14 slides. We're not in a rush here. And so perhaps next time I will go through the exploratory analyses of first order and second order effects. We'll go through some plots in R, although I will upload the code with this video, so you can, if you want to read ahead, you can. Kind of exciting. I'll be looking at a seminal case by Dr. John Snow, who analyzed cholera around water pumps in London. Nice interactive plots that are now possible. That's pretty cool. So a lot more exploratory analyses next lecture. So look out for those. And then after that, we will get into modeling. There will be a homework assignment posted fairly soon on geostatistical models. I hope you guys are all staying safe and things are going well. So stay warm, stay safe. I know there's snow in the forecast. Yeah, take care, guys.